Okay, so we've got another objective having to do with theorems, more theorems and definitions about continuity, including the intermediate value theorem, which will be important. So here's the left and right-handed definitions of continuity. And nothing surprising about them and nothing complicated about them. Basically, they are a matter of putting the little plus sign or the little minus sign on the A and saying, okay, you have continuity from the right if as x approaches a from the right, f of x equals f of a. So same old definition of continuity, but with an extra symbol on there, similarly with the left-hand limit. Now here's the big one. A function f is continuous on an interval. Okay, up to now we've talked mainly about continuity at a number a, but a function f is continuous on an interval if it be continuous at every number in the interval. If f is defined only on one side of an endpoint of an interval, we understand continuous at the endpoint to mean continuous from the right or continuous from the left. But if it would be continuous at every number in the interval, then we can say it's continuous on the entire interval. Instead of always using definitions 1, 2, and 3 to verify the continuity of a function, it is often convenient to use the next theorem, which shows how to build up complicated continuous functions from simple ones in a manner similar to the way that was done in college algebra. If f and g are continuous functions at a, they are continuous at a, and c is a constant, then the following functions are also continuous at a. So the sum function, the difference function, the function times a constant c, the product function, and the quotient function, if g of a not equal to 0. So in other words, and if you learn by hearing, this is your time to really catch what I'm saying here. Number 1, the sum of continuous functions is continuous. 2, the difference of continuous functions is continuous. 3, constant times a continuous function is continuous. The product of continuous functions is continuous, and the quotient of continuous functions is continuous. Continuous where g of a is not equal to 0. Okay, so it follows from Theorem 4 and definition 3 that if f and g are continuous on an interval, then so are the sum, difference, product, and quotient functions continuous on an interval. They're continuous at a number a, and if, for example, the sum function was continuous at every number a in an interval, then we're going to say that the sum function is continuous on the entire interval. The following theorem was stated as the direct substitution property. Okay, so we had that before, the direct substitution property. Any polynomial, okay, so a polynomial, so you're probably imagining some kind of quadratic, function. Any polynomial is continuous everywhere. That is, it is continuous on the set of real numbers, negative infinity to infinity. Okay, so if it's polynomial, you think about it, what polynomial could you graph without lifting your pencil from the paper? There is none. Any rational function is continuous wherever it is defined. Okay, so you've got a rational function that is a fractional function. It is continuous on its domain. So, you know, a rational function, y equals 1 over x. Okay, it's going to be continuous on its domain, wherever it is defined. It's not continuous at 0. It's not defined at 0. Right? 1 over x is not defined at 0. So the reciprocal function it's defined on its domain. Okay, whoops. So let's make a good picture here. So it's defined for all negative real numbers. So it's defined on the left, it's defined on the right, but it's not defined in the middle. It's continuous on the left, it's continuous on the right, it's not continuous in the middle. Okay, so the left branch, you could, you know, draw that without lifting your pencil from the paper. The right branch, the upper right, the one in the first quadrant, you can graph that without lifting your pencil from the paper. Obviously, such a thing cannot be said at 0, at x equals 0. That is, at the y-axis. As an illustration of Theorem 5, observe that the volume of a sphere varies continuously with its radius because of the formula v of r equals 4/3 pi r cubed. Shows that v is a polynomial function of r. So, in other words, the volume function, the volume which is a function of radius, that's a continuous function because it's a polynomial function. If a ball is thrown vertically in the air with a velocity of 50 feet per second, then the height of the ball is, well, it's another polynomial function right there. And so height is a continuous function of time. Most of the familiar functions are continuous at every number in their domains. Okay, so that it's very common to have a function, just any function you come across, it's common for it to be continuous on its domain. From the appearance of the graphs of the sine and cosine functions, okay, for example, let's take cos x. Okay, so y equals cos x. And let's see. Okay, so something like that. Okay. That looks continuous, right? I mean, it extends infinitely to the left and infinitely to the right. You can graph the whole thing without lifting your pencil from the paper. Same is true of sine. We know from the definitions of sine theta and cos theta that the coordinates of the point P in figure 5 are cos theta, sine theta. Cosine, if we're on the unit circle, cosine is the distance to the right of the y-axis. Sine is the distance above the x-axis. Of course, these things can be negative if, for example, we're below the x-axis. As theta approaches 0, so here's an angle theta, and it's getting smaller and smaller and smaller. Okay, angle theta getting smaller and smaller and smaller, and collapsing into the x-axis. As theta approaches 0, we see that P approaches the point 1, 0. And so cos theta approaches 1, and sine theta approaches 0. Thus, the limit as theta approaches 0 of cos theta equals 1, and the limit as theta approaches 0 of sine theta equals 0. Since cos 0 equals 1, okay, we're talking about continuity at a point, right? Since cos 0 equals 1 and sine 0 equals 0, the equations in 6, okay, here's 6, assert that the cosine and sine functions are continuous at 0. The addition formulas for cosine and sine, for example, here's the addition formula for cosine, then can be used to deduce that these functions are continuous everywhere. So since we know that the product of continuous functions is continuous, so that's true for these two products, the difference of continuous functions is continuous, we can say that cos a plus b is a continuous function because of the theorem. It follows from part 5 of theorem 4 that tan x, which is the quotient of sine x and cos x, is continuous except where cos x equals 0, right? That's 0. You can't divide by 0. So if cos x equals 0, tan x is not going to be defined, and so it can't be continuous there, but it is going to be continuous on its domain. So when cos x is going to be 0, that's the denominator, cos x for the tan function. That happens when x is an odd integer multiple of pi over 2. So pi over 2, 3 pi over 2, 5 pi over 2, and so forth. Also the negatives. So tan x has infinite discontinuities. What kind of discontinuity is it? Is it removable? No. Is it jump? No. It's an infinite discontinuity at those numbers. Okay, so here's a theorem which is powerful. It's kind of the next conclusion that we would naturally draw from the preceding discussion. The following types of functions are continuous at every number in their domains, right? We're not saying necessarily continuous on negative infinity to infinity, the set of all real numbers. Now, in the case of polynomials, that is true. But about all of these 4 kinds of functions, we can say that they are continuous at every number in their domains. Rational functions, are continuous at every number in their domains. Now, that's not 0 for 1 over x, okay, but because 0 is not in the domain, but every other number. Root functions, that's the case. Trig functions, that's the case. Continuous at every number in their domains. Another way of combining continuous functions f and g, right? I mean, all the other ways of combining functions were, just kind of the 4 basic operations. But now we also have another way that's we can do only with functions, not with numbers, and that is composition. F composed with G. This fact is a consequence of the following theorem. Theorem 8. If f is continuous at b, and the limit as x approaches a of g of x equals b, then the limit of the composition f with g equals f of b. Okay, so f is continuous at b, and the limit as x approaches a of g of x equals b. So this g of x on the inside of these parentheses right here as x approaches a, that g of x is approaching b. And so, of course, by hypothesis, the limit as x approaches b of g of x equals b, and so the limit as x approaches a of f composed with g of x equals f of b under this theorem. Intuitively, Theorem 8 is reasonable for the reason that we just said. If x is close to a, then g of x is close to b. And since f is continuous at b, if g of x is close to b, then f composed with g of x is close to f of b. Theorem: if g is continuous at a and f is continuous at g of a, okay, here's composition coming, we can feel it. G is continuous at a, f is continuous at g of a, then the composition f composed with g given by f of g of x is continuous at a. So that's exactly what we would expect. An important property of continuous functions is expressed by the following theorem, whose proof is found in more advanced books on calculus, and that is the big intermediate value theorem. Suppose that f be continuous on the closed interval ab. Big N is any number between f of a and f of b, so it's some y value, where f of a is not equal to f of b. There exists a number c, an x value, c, in the interval ab, open interval, such that f of c is equal to n. Okay, so here's the IVT, and it kind of goes like this. Okay, so let's say that we've got this mountain, goes like this. Okay. And this mountain is, say, 1,000 feet tall. Okay, 1,000. Okay. And this dude here, okay, this dude here is climbing the mountain, and it's, say, 12 noon when dude is at an elevation of, say, 100 feet. Okay. And he is going to get to the top of the mountain. Okay, so dude's climbing, and there's dude, top of the mountain. He's 1,000 feet. He's thrusting his fists into the air, and that happens at, say, 10 p.m. Okay. Question. Was there a time at which dude was at .500 feet? Okay, so here's 500 feet, Okay, here's 500. And again, by 10 o'clock, he's up here at 1,000. Okay. Was there a time at which he was at 500 feet? Of course there was. Okay. When he got right there, he was at 500 feet. There's a time that happened. We can estimate it. We can estimate it to be about 6 o'clock, maybe. So we can say, yes, there was such a time, and really what we're relying on is the intermediate value theorem. The intermediate value theorem states that a continuous function takes on every intermediate value between the function values f of a and f of b, which in our example, our mountain climbing example, those were 100 and 1,000. It's illustrated by figure 7. Note that the value n can be taken on once or more than once. Okay, so mountain climber, we only really saw one time that he was at 500 feet. But the mountain, it could have gone up and gone down, and there could have been multiple times at which he was at 500 feet. If we think of a continuous function as a function such that the graph has no hole or break, you can graph it without lifting your pencil from the paper, then it's easy to believe that the intermediate value theorem is true. In geometric terms, it says that if any horizontal line y equals n is given between y equals f of a and y equals f of b, as in figure 8, then the graph of f can't jump over the line. It must intersect because of the continuity. Because then you'd have to be able to lift your pencil from the paper if it's going to jump over the line, but we're assuming that can't happen. It must intersect y equals n somewhere. So going down the mountain, we know he's also going to be at 500 feet at some point. It is important that the function f in Theorem 10 be continuous. The IVT is not true in general for discontinuous functions. It might be true for some discontinuous function in a special case, but we can't count on it. We wouldn't make a theorem out of it. We can use a graphing calculator or a computer to illustrate the use of the IVT. Figure 9 shows the graph of f in a viewing rectangle, -1 to 3 in the horizontal, -3 to 3 in the vertical. You can see that the graph crosses the x-axis between 1 and 2. Okay, so zero feature works. Figure 10 shows the result of zooming in to the viewing rectangle. Okay, now we've narrowed it way down from -1 to 3 to 1.2 to 1.3, and in the vertical we've narrowed it way down. So it's interesting that the intermediate value theorem plays a role in the very way these graphing devices work. Okay, so we're going to learn something now about your graphing calculator. A computer calculates a finite number of points on the graph by necessity and turns on the pixels that contain these calculated points. It assumes that the function is continuous and takes on all the intermediate values between two consecutive points. Now here's the interesting part. The computer therefore connects the pixels by turning on the intermediate pixels. Turning on the intermediate pixels. Tricky. And that will get it done for 1.8 and chapter 1 of Stewart's 7th edition of calculus. And in the 8th edition, early transcendentals, he has a few more sections that we will begin to cover in the next video.